Hello students, welcome to 6th lecture of chemical bondings and molecular structure. In previous lecture we discussed about ionic solids and now on this point onward we will start with bonds. In this point we will discuss about bond parameters like bond length, bond angle, bond enthalpy, bond order, resonance, polarity, etc. Okay, so step by step we will discuss about each and every parameters related to bonds. So let us start with bond length first. So bond length is defined as the equilibrium distance between the nuclei of two bonded atoms in the molecule. That means in simple word we can say that bond length is a distance between two nuclei of two atoms attached with each other. Okay, suppose you have hydrogen, then let us assume hydrogen as a spherical ball like shapes. So first spherical hydrogen atom and second spherical hydrogen atom will be in contact like this. Okay, so that means we have two different balls which are touching each other. So how can we find bond length of this type of spherical structure? Simple thing is distance between their nucleus. Okay, suppose these are the nucleuses of both of the hydrogens and distance between them is called bond length. Okay, so this is the bond length of given molecule. Now in this thing distance is okay, but what is equilibrium distance? Okay, so equilibrium distance is you can assume molecules as a shaking spheres attached with each other. That means they are not static. If you can observe the molecule at microscopic level, then depending on their energies they are continuously shaking. That means they are moving closer to each other and away from each other continuously. That means suppose we have two different situations for hydrogen, given hydrogen. Suppose first situation is they are stretched and move away from each other like this, and then bond contracted and distance decrease like this. So this is the maximum and this is the minimum. Okay, we have two different type of lengths and continuous shaking, that means stretching and releasing. Just like suppose you hold a rubber band in your hand, initially the length or a distance between your hand holding rubber band without stretching is, let us say, 2 centimeter. When you stretch the rubber band, distance between your hands increases and let us say it is 5 centimeter. Okay, so this represents stretched position and this represents resting position. So equilibrium distance between average of maximum and minimum, it will be bond length. So keep in mind, bonds are not steady. They have multiple different type of motions. As for example, stretching, and suppose you have angular molecules, then they will bend. That means suppose our angle is let us say 90 degree. So it is not constant 90-degree angle. Sometimes it will be 60 and sometimes it will be 120, and average of highest and lowest angle will be considered as bond angle. We will discuss it in that topic. So bond length is defined as equilibrium distance between two nuclei of two bonded atoms in the molecule. Now bond lengths are measured by spectroscopy, X-ray diffraction and electron diffraction techniques, about which you will learn in higher classes. Okay, so we are not going to discuss them in detail, but these are the methods which can detect the different type of parameters of microscopic objects like atoms and molecules. Each atom of the bonded pair contributes the bond length. In the case of covalent bond, the contribution of each atom is called the covalent radius of that atom. So this is a simple image representing the bond. So as we can see, radius of, we have two different atoms A and B here. So radius of A is RA and radius of B is RB. So total distance between these two center atoms nuclei will be Ra plus Rb, and Ra plus Rb represents bond length of given molecule AB. So AB has Ra plus Rb bond length, in which contribution from A is Ra and contribution from B is Rb. So as mentioned here, in the case of covalent bond, the contribution of each atom is called the covalent radius of each atom. So covalent radius of A will be Ra and covalent radius of B will be RB, and we can call them as a radius of atoms as well because it is covalent radius of them. So covalent radius is measured approximately as the radius of atom's core which in contact with the core of the adjacent atom in bonded situation. The covalent radius is half of the distance between two similar atoms joined by a single covalent bond. That means if you want to find the radius of atom, you cannot find it individually. That means you cannot separate out a simple hydrogen atom and then you can measure its radius. So how can we find the radius of atoms? Simple thing, find the molecule of given atom. That means suppose you want to find the radius of oxygen, then you have to use oxygen molecule. Find the radius of oxygen molecule, bond length of oxygen molecule, and it contains similar type of atoms, and divide it with half. That means half of the length represents radius of given atom in the same molecule. The van der Waals radius represents the overall size of the atom, which includes its valence shell in the non-bonded situation. Okay, so it is the method to find the radius of single atoms. Further, the van der Waals radius is half of the distance between two similar atoms in separate molecule in solid. The covalent and the van der Waals radius of chlorines are depicted in figure 4.2. So as you can see in these images, we have two different type of atoms mentioned here. Both of them are Cl2 molecule, but their van der Waals and covalent radiuses are mentioned. So first of all, as we can see here, two different chlorine molecules are separated with some white circles. Inner circle actually represents the chlorine atoms. But notice we have one more circles around these chlorine molecules. Okay, so what these circles represents? So actually it represents these two chlorines are in gaseous state. So that means similar nature will repel each other. That means two different molecules of chlorine actually do not feel strong attraction towards each other. So attraction between them is called van der Waals attraction, and it has some limit. If you cross certain limit, then attractive forces will be overcome with repulsive forces, and repulsive forces won't allow to decrease distance after a certain point. So this outer line actually represents that limit. When we place two different chlorine molecules close to each other, so there is a limit how the minimum distance is possible. So this is possible minimum distance. So distance between two adjacent molecules nuclei. Okay, so this is the distance from this point to this point, which is 360 pm. So half of it will be called covalent radius. As you can see here, it is 180, and the covalent radius will be the distance between the atoms of same molecule. Okay, so this will be the bond length, and half of this bond length is called covalent radius. So bond length is 198 and half of 198 will be 99. So the covalent radius is a half of the distance of two adjacent atoms in the same molecule, and van der Waals radius is half of the distance of two adjacent nucleuses of two different molecules. Okay, so as you can see here, we have distance between two atoms in the same molecule, and these two represents distance between two separate molecules. And some typical lengths of single, double and triple bonds are mentioned in table 4.2. So you can compare, and you will notice as the bond number increases, that means single bond, that means it has one bond number, two that means double bond, and triple bond. So as the number of bonds increases within the same atom, lengths will decrease because two different atoms feels stronger attraction towards each other with increasing bond number. So these are the mentioned, and bond length of some common molecules are given in table 4.3. Okay, so you can see and compare, and if you find any difficulty, then you can ask. And the covalent radii of some common elements are listed in 4.4. Next is the bond angle. So it is defined as the angle between the orbitals containing bonding electron pairs around the central atom in a molecule or complex ion. So as mentioned earlier, complex ion will be a topic of 12th. You will learn about it in 12th standard. Bond angle is expressed in a degree which can be experimentally determined by spectroscopic methods. It gives some idea regarding to the distribution of orbital around the central atom in molecular complex ion, and hence it helps us in determining the shape of molecule. So if you can find the angles between the atoms, then we can predict the shape of molecule as well. For example, HOH bond angle in water can be represented as under. So experimentally obtained value of angle between the HOH is 104.5 degrees. So we can predict the shape of molecule. We have only 3 atoms here, and angle between HOH is 104, then it must be angular molecule as shown in here. Central atom will be oxygen and 2 hydrogens are attached with it. Next is a bond enthalpy. So it is defined as the amount of energy required to break 1 mole of bond of the particular type between 2 atoms in gaseous state. That means, suppose, let us use the same example of Cl2. Suppose you have Cl2 gas. Then you need 1 mole of that gas, and amount of energy required to all of these bonds is called bond enthalpy of Cl2. So it will be used in kilojoule per mole unit. So the unit of bond enthalpy will be kilojoules per mole, because we have to apply energy in kilojoules and total used amount of molecule is in 1 mole. For example, H bond H enthalpy in hydrogen molecule is 435.8 kilojoules. That means if you have 1 mole of hydrogen gas, then you have to apply 435.8 joules of energy to break all of these bonds. Or in reverse, we can say that if you have 2 moles of hydrogen atoms, then when these 2 moles of hydrogen atoms combines and it produces 1 mole of hydrogen gas, H2 gas, it will release 435.8 kilojoules of energy. Okay, so simple reaction is mentioned. If you have H2 molecule, then you separate it into H atoms, then enthalpy of this reaction will be 435.8. As you can see, value of enthalpy is positive. It represents this reaction is endothermic. It requires energy. Similarly, the bond enthalpy of molecules containing multiple bonds, for example O2 and N2, are as under. So as you can see, requirement of energies generally increases with increasing bonds. If you have double bond, then as in this case 498 kilojoules of energy is required, and if you have triple bond like nitrogen, then 946 kilojoules of energy is required. So with increasing bond, requirement of energy also increases. It is important that the larger the bond dissociation enthalpy, stronger will be the bond in the molecule. Okay, so higher value of energy required represents you need more energy to separate them, or it requires more amount of energy or more force to separate. It represents stronger bondings. For heterogeneous diatomic molecule like HCl, heterogeneous that means two different particle containing, homogeneous that means similar, and hetero that means different. We have, so as we can see here, energy requirement is 431 kilojoules. To separate 1 mole of HCl from each other, you need 431 kilojoules of energy. In case of polyatomic molecule, that means which contains more number of atoms, more than 2, the measurement of bond strength is more complicated. For example, in case of H2O molecule, the enthalpy needed to break the 2OH bond is not the same. That means if you break the first bond, then requirement of energy will be different, and after breaking first bond, when you try to break second bond, energy requirement will be different. As we can see here, when we break the first bond between the hydrogen and oxygen, at that time requirement is 502 kilojoules. But when we try to break second OH bond, requirement of energy decreases. It is 427. Why this thing happens? Because when we break the first bond, we are actually unstabling the molecule, and because now our molecule is unstable, it has already some amount of energy. So extra requirement of energy decreases and we need to put less energy to break the second bond. Understand it this way. Suppose you have a room which has four walls. Okay, so when you try to break the first wall, requirement of energy will be maximum because full structure is stabilized and it is supported from all the side. But suppose you already broke two walls, then trying to break third wall will be comparatively easy task because structure is unstable. So it can collapse on itself, but still suppose you need to put some energy to break third wall. But when you break the third wall, fourth wall will collapse automatically. Okay, because it is completely unstable structure. It is supported from one side and three sides are completely unsupported, so fourth wall will break on its own. Okay, so as we break the bonds, our structure or molecule becomes unstable, and that's why requirement of energy decreases with each bond breaking. Okay, so difference in enthalpy value shows that the second OH bond undergoes the some change because of the change in chemical environment. This is the reason for some difference in energy of some OH bonds in different molecules like C2H5OH and water. Therefore, in polyatomic molecules, the term mean or average bond enthalpy is used. Mean bond enthalpy or average bond enthalpy. It is obtained by dividing the total bond dissociation enthalpy by the number of bonds broken. As explained below, in the case of water, we have two different enthalpies, 502 and 427, and we will take average, which is 464.5. So this will be considered bond dissociation enthalpy for water molecules. Bond order. In the Lewis description, the covalent bond, the bond order is given by the number of bonds between the two atoms in the molecule. The bond number, for example, in H2 with a single shared electron pair, in O2 with two shared electron pair, and N2 with three shared electron pair is 1, 2 and 3. That means if two electrons are present between two different atoms, its bond order will be 1 because we have one pair of electron. If you have two pairs or four electrons, then it will be 2, and if you have three pairs or six electrons between two atoms, then it will be 3. Bond angle will be 3. So similarly in CO we have three shared electron pairs. The bond angle will be 3. For nitrogen, bond order is 3 and its enthalpy of atomization or bond dissociation enthalpy is 946. In symbol of enthalpy, A represents atomization. That means when you convert molecules into atoms. Being the one of the highest of diatomic molecules. Diatomic, that means two atom containing molecules. Isoelectronic molecules and ions have identical bond order. For example, F2 and O22 minus have bond order 1. N2CO and NO plus have bond order 3. Now isoelectronic, that means same number of electrons containing. So if you try to find the number of electrons in each, as for example, first comparison between F2 and O22 minus. So one fluorine contains 9 electrons, so two fluorine contains total 18 electrons. In case of O2, one oxygen contains 8 electrons, so two oxygens will have total 16 electrons and it carries -2 charge. That means you have to add 2 more electrons, so total number of electrons will be 18. Now let us compare N2CO and NO2. Nitrogen, one nitrogen atom contains 7 electrons, so 2 will have 14 electrons. In case of CO, carbon contains 6 electrons, oxygen contains 8 electrons, so total 6 plus 8, 14. In case of NO plus, nitrogen contains 7 electrons, oxygen contains 8 electrons, so total we have 15 and it carries positive charge, so you have to remove one electron, so total number of electrons will be 15. So all of them carries 14, it will be 14, so all of them carry same bond number, which is 3. Bond order will be 3. General correlation useful for the understanding the stabilities of the molecule is that with increasing bond order, bond enthalpy increases, bond length decreases. Now what is the relationship of stability with given terms: bond order, bond enthalpy, and bond length. So please note down that stability of molecule is directly proportional with bond order and bond enthalpy. That means if bond order increases or bond enthalpy increases, it represents stability of molecule is increasing. But bond length is inversely proportional with stability. If bond length increases, stability decreases. Assume it like this: suppose you have a rubber band in your hand. So if rubber band is in resting position, that means distance between 2 points in that rubber band will be minimum. At that time, strength of rubber bond or stability of rubber bond will be maximum. So let us assume you can stretch the rubber bond up to 10 centimeters, and if you try to stretch it more than that, it will break. So if you increase the distance between 2 points on rubber band, that means you are stretching it, and if you are stretching it, its stability decreases. It will become unstable, and after a certain limit, if you stretch it more, it will break. So distance, increasing distance actually decreases the stability. Okay, just like rubber band, same is true for our molecules. So if bond length increases, stability decreases. So bond length and stability, they are inversely proportional, and bond order, bond enthalpy, and stability, they are directly proportional. With increasing value of bond order or bond enthalpy, stability increases. So till this point, if you find any difficulties, it is comparatively easy points. It is not as hard. So if you still find any difficulty, feel free to ask. And the next topics will be discussed in next lecture.